66 million years ago, a massive asteroid wiped out the entire dinosaur species in a single catastrophic impact. It's a harsh reminder that our beautiful planet will not always be a perfectly safe sanctuary. If a similar event happened today, human civilization would face a total collapse. To prevent this, scientists and visionaries are now arguing that the only way to secure our future is to live on more than one planet. Look at Venus, our closest neighbor. It is 450 degrees Celsius with sulfuric acid clouds. Going there means instant death. Moving outward, gas giants like Jupiter and Saturn offer no solid crust to build a colony on. This image from the Viking lander shows exactly why Mars is our only logical candidate. It has a solid terrestrial surface. A day lasts about 24 hours, it experiences distinct seasonal changes, and holds massive water ice reserves. Mars is the only viable lifeboat in our solar system. But actually getting there, and surviving once we do, presents the absolute hardest engineering challenge humanity has ever attempted. Because Earth and Mars orbit the Sun at different speeds, the physical distance between them is constantly changing. We can only launch during a highly specific alignment window that opens once every 26 months, resulting in a travel time of 7 to 9 months. If a critical life support system fails on arrival, the crew cannot just turn the ship around. The orbital mechanics dictate that the first missions will be strict one-way tickets. And the moment an astronaut steps outside, the planet goes on the offensive. The Martian atmosphere is 1% the density of Earth's, and 95% of it is toxic carbon dioxide. Without a pressure suit, a human would fall unconscious in 15 seconds and physically die in just 2 minutes. Then the extreme cold sets in. Mars averages negative 60 degrees Celsius, with localized drops down to negative 125 degrees. That is cold enough to freeze human blood. This cross-section shows our Earth's magnetic field blocking harmful solar rays. Mars lost its magnetic field billions of years ago. Cosmic and solar radiation directly strikes the surface. Spending 1 year on Mars exposes a human to the same amount of radiation they would absorb in 8 years on Earth. Mars is a hostile, active antagonist. It is chemically and geographically designed to kill us. If we want to live there, we have to entirely hack the planet. The first barrier to hacking Mars is pure economics. Transporting heavy cargo across deep space using traditional single-use rockets costs hundreds of millions of dollars per launch. This is SpaceX's Starship. It is the largest rocket ever constructed, designed specifically to brute force the distance problem by carrying a massive payload of 100 to 150 metric tons directly to the Martian surface. In the past, rockets were discarded after a single use. By landing and relaunching the Starship booster repeatedly, the cost of manufacturing a new rocket for every flight is eliminated. SpaceX aims for this efficiency to eventually bring the price of a ticket down to the cost of an average home. But we cannot afford to ship thousands of tons of steel and concrete to build entire cities. Instead, engineers rely on a concept called in situ resource utilization, or ISRU. We have to build with what is already there. Before humans arrive, autonomous robots will land on the surface. They will act as massive 3D printers, scooping up the iron-rich Martian regolith, the dirt that gives the planet its red color, and extruding it to build the structural shells of our habitats. To counter the extreme temperature swings and block the lethal cosmic radiation, these structures must be built a few meters underground. We will use the hostile planet's own soil as physical armor to protect the first human colonies. Surviving long-term requires an endless supply of water. We need it to drink, to split into breathable oxygen via electrolysis, and to manufacture the methane-based rocket fuel needed for a return trip. Fortunately, Mars is hiding millions of cubic kilometers of water ice, locked at the poles and buried just a few meters beneath the soil. Teams at NASA and SpaceX are designing thermal drills that will bore into the ground, melt the subterranean ice, and pump the liquid water to the surface, where it can be purified and stored. Food presents a different challenge. The Martian dirt contains high levels of chemicals called perchlorates, which are highly toxic to plants. Traditional agriculture is physically impossible. This image from the International Space Station shows the exact solution. Using hydroponic and aeroponic systems, we can grow vegetables without any soil at all. The plants are suspended in nutrient-rich water inside controlled pressure domes, soaking up artificial LED sunlight. Extracting subsurface water and running soil-free farms are the two essential engineering milestones. Once those systems are online, the Martian colony cuts the umbilical cord to Earth and becomes entirely self-sustaining. If we can survive the first few decades, the objective shifts from bare survival to planetary mastery. The ultimate long-term project is terraforming, engineering the Martian atmosphere so humans can walk outside without a spacesuit. To thicken the atmosphere and trap heat, scientists have proposed deploying giant mirrors in Martian orbit to focus sunlight onto the poles, or building specialized factories that continuously pump out greenhouse gases to trigger artificial global warming. But even if we warm the planet and generate oxygen, one permanent variable remains. Gravity on Mars is only 38% as strong as Earth's. Over generations, living in low gravity will physically alter how bone density and muscle mass develop. Martian-born children will have different biomechanics. They will move differently, look differently, and represent a distinct evolutionary branch of humanity. Establishing this colony could cost upwards of $1 trillion. It's a massive price tag, but the technology developed to extract water, purify air, and grow high-yield crops in extreme environments will immediately benefit Earth while providing a necessary safeguard for human survival. In 1903, the Wright brothers managed a flight that lasted just 12 seconds. Only 66 years later, we were walking on the moon. In a single human lifetime, we moved from the first beach takeoff to the lunar surface. Today, SpaceX is preparing its next Starship test, and NASA is studying Martian soil samples in real time. The next time you see that reddish dot in the night sky, remember that for the next generation, it may no longer be a destination, but a home.